Welcome back to our series on probability theory. I'm Mark Ledbetter. This is lecture video 42, part B. We are discussing univariate transformations. This is part 4 of that section. So far, we've gone over how to do inverse transformations for discrete random variables, which there is no theorem, but we know that we have to add up if it's k to 1 relationship, then we have to add up probabilities. If it's a 1-to-1 relationship, then we just simply have to map 1-to-1 the probabilities from x to say y equals u of x, some function of x. Then for continuous distributions and random variables, we discussed the CDF method, and then we talked about the univariate transformation theorem for 1-to-1 functions, and we did a couple of examples there. So we're going to discuss a k to 1 function, and then the CDF theorem. So a inverse transformation theorem for k to 1 functions of x, and the CDF theorem. So the transformation theorem, we used that in the examples, and last time we used this example and we found this very important result. Again, these transformations make life easier for us in many cases because we may not be able to or easily calculate something using the distribution, but if we transform it to a different distribution, we may be able to make the calculations easier or at all sometimes. Okay, so we found this result that if x is uniform from pi equals, or from negative pi over 2 to pi over 2, then the function of x, y equals the tangent of x, that has a standard Cauchy distribution. And here is the PDF of the standard Cauchy distribution. Okay. So let's talk about this k to 1 transformation theorem for continuous random variables. So we're going to let x have a PDF f of x, and y is going to be a function of x that is a k to 1 function. That means we need k different transformations here. Okay? So for each segment of x, there will be a different transformation. So we said that y is u of x, and so x is going to be the inverse of u on y. And so we're assigning that w of y as that inverse function. But now we have w1, w2, all the way up to wk of y. And these are the k inverse transformations. So then the PDF of y is going to be the sum of all the transformation theorems. So we're going to use our previous transformation theorem on each of these segments. So we'll have k of them, and we will add them together. So we take the function f of, and in place of x, we will put wi sub I of y, which is the inverse transformation x equals that on that range, whatever this range of x is where this is true, times the absolute value of the derivative of that inverse transformation. So we do that. So we do this. This is the transformation theorem for the 1-to-1. So we do that where we have a 1-to-1 inverse in that section of x, and then we take that and we do this for each of those pieces, the k pieces, and we add them together. And that gives us the PDF, the overall PDF of y. So again, I know that this is sometimes notation heavy. So let's do an example. We're going to do a very important example. We're going to let x have a standard normal distribution. The mean is 0, the variance is 1. And let our function y be x squared. Okay? And so we want to find the PDF of y. So y is equal to u of x, which is x squared, and we take the inverse, which is the square root of both sides, to get x. But when we do that, we get that x is plus or minus the square root of y. And so we have to look at this, and we say that, well, when x is positive, right, then x is the square root of y. And when x is negative, x is the negative square root of y. And so this is w1 of y, and this is w2 of y. And then we have that the range of x is from negative infinity to positive infinity, but the range of y, you notice, y is always positive or 0, so it's from 0 to infinity. Okay. Now, f of x is a standard normal, so we need to know the standard normal PDF, which is 1 over square root of 2 pi e to the negative x squared over 2. And x is in the real numbers, from negative infinity to positive infinity. Okay? So now, we're going to say that y1 sub y, we've set that w1 of y is the square root of y, positive square root of y. So we can rewrite that as y to the 1/2. So w1 of y equals 1/2, not 1/2, y to the 1/2. When we take the derivative of that, we multiply 1/2 y, and then 1/2 minus 1 is negative 1/2. So that's our derivative of w1. And w2 is going to be the negative of that, because we have negative square root of y, or negative y to the 1/2. We take the derivative of that, we get negative 1/2 y to the negative 1/2. And notice that the absolute value of these two functions is the same. There's going to be the positive 1/2 y to the negative 1/2. That's for I equals 1 or 2. Then the PDF of y, g of y, which is the PDF of y, is going to be the sum from I equals 1 to k, that k is 2 here, f of wi of y, wi prime of y, absolute value. Now, so everywhere we had x, we have to substitute in for wi of y. So for the first section, we have 1 over square root of 2 pi e to the negative y over 1/2. Remember, it's x squared is going to be the square root of y squared, so which is y. So we have negative y over 2 as our exponent, times w prime of y, and w1 prime of y is 1/2 y of negative 1/2, and it's the absolute value. And so then we have the similar thing for, it turns out to be identical for the other, because once we square x, which is negative y squared, I have to be careful, I just put it in the wrong spot, the negative. So if x equals negative square root of y, we square both sides, x squared is still positive y. And so we had the negative sign up here, but we get the exact same thing for this as we did for this. So we have these two expressions, so we end up with 2 times that, and we end up with this expression here, which is 1 over the square root of 2 pi, y to the negative 1/2, e to the negative y over 2. This reminds us of a gamma. This is a gamma function. Gamma distribution, not function, distribution. So now we've got, remember, you need to know that the gamma of 1/2 is square root of pi. And so, and then we have square root of 2 is 2 to the 1/2. And I can rewrite this using the gamma distribution and the 1 minus. So I have 1/2 minus 1 in the exponent. I need alpha minus 1. And then y negative e to the negative y over 2. 2 is theta. So theta equals 2. And alpha is going to equal 1/2. And so I have gamma 1/2, 2. And that is a chi-squared 1 distribution. So we find the same result that we found before using the different method where we use the transformation. We said that if z, so if we have z is a normal distribution, standard normal, then z squared is a chi-squared 1. So we just proved it with the transformation theorem. We did this with the CDF method, okay, where we looked at the CDF and that was the method that we used there. So we've just done that same method, or we've just done the same thing with the transformation theorem. But because it's a square, we had to use the k to 1 version of the theorem. Okay, so I hope that helps you understand that part of the transformation theorem, doing it in pieces. You have to be very careful. You notice that I drew a picture of y squared and labeled it carefully in order to make sure that I get these regions correct for x, the inverse. Okay. Now, this theorem for the CDF is extremely important. We're going to say that x has the CDF capital F of x, and it's continuous type random variable. And it's strictly increasing, okay, on the support of x between a and b. Then the random variable y, where y equals f of x, has a uniform distribution, uniform 0 to 1. This is a very important theorem. So as long as the strictly increasing, as long as it's a strictly increasing CDF, then it's y equals capital F of x. The CDF has a uniform distribution. It goes between 0 and 1. Remember that from the definition of the CDF, we said that it would be 0 if x is less than, let's say, a, if that's the beginning of it. And then we'd have some function when, let's say, x is between a and b. And then it would be 1 when x is, say, greater than or equal to b. So we could have several stepwise functions here, or piecewise functions. And if it's piecewise, it's going to be stepwise. It's going to be a step function. And it's always right continuous. So coming from the right, it's continuous. So we could have something like that. But that's not strictly increasing, is it? So if we have something that is strictly increasing from 0 to 1, or from, so it goes from y equals 0 to 1. If it's strictly increasing, then f has a uniform distribution. So now we're going to say that f of a is equal to 0, and f of b is equal to 1. And this is the property of the CDF. Then f of y is equal to the probability that y is less than or equal to little y. And that can be written as the probability that f of x is less than or equal to little y for y between 0 and 1. And for f of x, capital F of x, it's always between 0 and 1. Okay? Note that this set, f of x less than or equal to y, is identical to, I'm taking the inverse transformation. So x is less than or equal to the inverse transformation f on y. So then the probability that y is less than or equal to y is the probability that x is less than or equal to f inverse of y for y between 0 and 1. And then I can now take the f function of the inverse, and that gives me y. Right? So this is equal to, so I'm not taking, this is actually what we've defined here is this probability that x is less than or equal. This is the CDF of this quantity. Remember that f of little x is equal to the probability that x is less than or equal to quantity little x. So this is in fact f of this quantity, whatever we're less than or equal to, which is this. When I take f of the f inverse, I end up with the with y here. So for y between 0 and 1. So the probability that x is less than or equal to x is equal to f of x, right? And this is the CDF, this here is the CDF of the uniform 0 to 1. If I take the derivative of f prime, so f of y, if I take the derivative of that, I get little f of y prime, derivative of y, dy of y is equal to 1. And so I have f of y is equal to 1, and y is between 0 and 1. This implies that y is a uniform 0, 1. That's what it looks like. Okay, and so right here we have proved that this theorem is true. Okay, so that's it for this section. So I hope that you will take time to review the examples and look through them, because I know that most students struggle to put this information, absorb this information. Okay? So please don't forget to scan and upload your lecture notes before midnight, the date listed on the course calendar. If you have questions, come to virtual office hours. I'm happy to help you. If you need help before you can come to office hours, by all means, email me. But email me a picture of the problem so that I have that handy, because I may not otherwise, and a picture of your work so I can see how you're approaching it. And I will be happy to help you, and I will be able to help you through email. Please take care of yourself, stay safe, and we hope to see you next time.